Well, good afternoon. First of all, Fernando, thank you for the introduction, the kind introduction that you just made. And I also want to greet the people who are attending this webinar. I see that we have 48 people who are attending, so hello to everybody. And Fernando already gave you some instructions regarding submitting questions. So I will start now speaking about the topic of super premium electric motors. So what is a super premium motor? The super premium motor is a motor which has lower losses, between 15 to 20% lower losses than an i3 motor. And according to the terminology of the IEC, International Electrotechnical Commission, i3 in USA is called NEMA, so there is sort of equivalence in designation. So there is still a new class not yet fully defined, which is ultra premium class C5, that at least must have 15% lower losses in relation to super premium. So this graph shows the IEC standard 6003431, the last version of which was published in 2014, and it should be emphasized that only in 2008 a standard on motor efficiency classification was published. So this shows a bit of low attention to efficiency in motors, but fortunately in the last couple of decades around the world there has been a lot of work to improve efficiency of motors. So you can see in this graph that we have 4 efficiency classes which are fully defined: I1, I2, I3, I4, and I5 is tentatively defined. That's the dotted line. In terms of designation around the world, we have different names. So IEC standard applies all over the world, but NEMA in USA calls i3 motors premium and motors above premium super premium. In Australia and New Zealand they use E3 and E3 plus. In Brazil they use also i3, and in China they use grades like for i3 grade 2 and for super premium grade 1. How has the market been evolving in Europe? As a matter of fact, we can call it a success story if we think that 20 years ago, in 1998, 2/3 of the motors sold were below I0. So in less than 20 years, basically we have motors below I1, that's I0 motor, removed from the market, and we have now in 2016 we have the motor market being majority taken by I2 energy efficient motors and by 3 energy premium motors. Super premium motors are still very few. It's estimated about 0.5% of the motors sold in Europe in 2016 are super premium motors. But in any case, we see that a very substantial market transformation has occurred in Europe in the past 20 years. So this is definitely good news. And we are referring to motors from 0.75 to 375 kilowatt. In terms of the situation worldwide, here we have a map, a timeline, looking at what has happened in the past 20 years, and we see that the first countries introducing mandatory minimum efficiency standards were USA and Canada, but since then we have been assisting at the implementation of motor efficiency standards around the world, and namely the premium efficiency IE3 is now mandatory in North America, Europe, Turkey, Saudi Arabia. So it's really good news that we are seeing this spread of efficiency movement. In terms of evolution of the European motor market, in 2012, the motor was dominated by IE2 motors, energy efficient motors, and we see that in 2020, we see that the market will be mostly dominated by premium motors, by IE3 motors. About more than 3/4 of the motors sold in 2020 in Europe are estimated to be IE3 premium motors. IE4 motors, the super premium motors, are estimated to be about 4%. So we see now we have last year 0.5. In 3 years' time, we expect the percentage not to be dominant, but in any case, it's a significant change, reaching an estimated 4% of the market in 2020. Another interesting forecast is the penetration of converter-fed motors, because of the perception that the converter-fed motors can have better efficiency and better performance, and at the same time the converters have been decreasing in price. We see that there is an estimation that by 2020, about half of the motors sold in Europe will be driven by electronic converters. And this is very important because some motors, some very efficient motors, need an electronic converter. So some motors will be used direct online, but some motors will be used because of efficiency and performance reason with electronic converters. So we see that about half of the market in 2020 will be taken by these variable speed applications. So in terms of achieving efficiencies above IE3, we see to reach either super premium or ultra premium performance, IE4 or IE5, we have different candidates to achieve these performance levels. There are already on the market induction motors which are able to achieve IE4 performance. We have line start permanent magnet motors. We have permanent magnet motors driven by electronic converters. We have synchronous reluctance motors with variable speed drives. For reaching IE5, we have permanent magnet motors driven by electronic converters. We have in development permanent synchronous reluctance motors with variable speed drives, and we have also at least one manufacturer as stated that are able to achieve IE5 performance with induction motors. So this slide shows a sort of possibilities in terms of technologies to achieve efficiency levels, and we see that to achieve this super premium IE4 and ultra premium performance, we have a variety of technologies which can be used to reach these efficiency levels. Some of these options seem more adapted for lower power motors, but in any case, we have different possibilities to achieve these very high efficiency levels of performance. So at the moment, we have already several manufacturers which are able to meet both IE4 and IE5, so it's not a pie in the sky. Some years ago, there were some skepticism about managing to go up and reach this ultra premium performance, but we are there. We are there, and we are seeing competition among manufacturers with different technologies which are being able to move up the efficiency scale. So in terms of motor losses, we have electric losses associated with conduction in the copper. We have the magnetic losses, which both the electric losses and magnetic losses, you can improve them by using more materials. In the case of magnetic losses, there has been some improvement in magnetic materials. I will speak more later about this topic. Mechanical losses also due to friction bearings and ventilation, and we are seeing some marginal improvements in ventilation design and in bearing design. And stray load losses is basically through the improvement of motor design and better manufacturing. So this graph shows how the different losses are distributed in the motors, different types of losses as a function of motor power. And there is here one type of losses which I want to call your attention, which is the rotor losses. And basically we have magnetic and Joule losses in the rotor because of rotor slippage. So basically the induction motor does not rotate at the same speed as the magnetic field, and because of this slip you have currents in the rotor. When you change technology from induction to synchronous motor technology, you are able to achieve two advantages. First of all, there is no slippage. The rotor is rotating in synchronism with the rotating magnetic field. And on the other part, because there is no slippage, you don't have electric and magnetic losses in the rotor. So basically, from moving from induction process to synchronous process, you are able to cut losses by about 20%. So this is an important advantage of synchronous motor technologies. So this is a cutaway view of induction motor and showing the components where improvements have been made in the last decades, and it must be said that manufacturers have done a fantastic job in cutting motor losses by about 50% due to more quantity of active materials, better design, improved manufacturing. So induction motor is very robust, has a fairly high efficiency, is inexpensive. So I would say that for many applications which do not need, which require direct online starting, I see induction motor as playing a very important role in the future. So we see also here something that's important for this seminar, is that some losses on the motor are constant, like the magnetic losses and mechanical losses, whereas the copper losses and stray load losses are variable. And synchronous motor technologies have better part load performance. And this is because of the reduced role of the fixed motor losses. So when you are looking at the comparison of efficiency between induction motors and synchronous motor technologies, typically the efficiency difference becomes larger as the load becomes smaller, because the fixed losses play a smaller role in the synchronous motor technology. So again, this is a cutaway view of an induction motor showing the components and what can be done in terms of improving efficiency. in the magnetic steel, there have been some developments on amorphous steel, but I'm only aware of a manufacturer who has been able to produce a commercial motor using amorphous steel. Amorphous magnetic steel has a reduction of about 70% of the magnetic losses, but the manufacturing process is not so easy, requires special machinery, so the potential is there. So if an efficient manufacturing process can be developed to have motors which use amorphous magnetic steel in the future, because the basic price of the material is not very different from conventional magnetic steel, but the manufacturing process is very different because the laminations have about 25 microns. So this is about 12 times less than a lamination of steel lamination used in a normal motor. Another way to improve efficiency of induction motors is using copper cage rotors instead of aluminum. Copper is a better conductor, so you can improve efficiency of the motor or make the motor more compact. So you have these two possibilities when you are using copper rotor motors, and some manufacturers around the world have been using these motors to produce higher efficiency and more compact induction motors. An interesting application of this copper rotor motor is in electric vehicles made by Tesla. They have been using copper rotor motors in their cars. So this is another example of a small motor with copper rotor. As a matter of fact, we tested in our laboratory two motors with the same stator and different, one with aluminum cage and another with a copper rotor cage, and we see that there is a significant efficiency difference between the copper rotor motor and the aluminum motor. A recent development that has happened not so recently, it was in the 80s, both in USA and Japan, permanent magnets were developed with very significant improvement over conventional magnets using the so-called rare earth alloys. So the rare earth magnets, the most widely used type of magnet, is composed of iron, the main component, neodymium, and boron. And this has a very high energy density and also is very hard to demagnetize. And this basically created a new tool for the designers of motors and generators to be able to design very high efficiency machines, very high efficiency and compact machineries. So the other permanent magnet material that is being used in large-scale motor manufacturing is ferrite, and ferrite is a low-cost material that has much lower performance than rare earth materials, but it's the price for the same energy density is about the price is 20 times less, but the energy density is much lower. So we have this technology development that influence the development of new products. Rare earth materials, probably you have been hearing about this. There are some market issues regarding too much dependency on imports from China, and there has been problems of price escalation and market rigging a few years ago, which makes some manufacturers uneasy about relying too much on these materials. One type of one of the first super premium motors that appeared in the market maybe 6-7 years ago, was the line start permanent magnet motor. Basically, is a motor that has the same frame size of an induction motor, but we have a hybrid rotor in which we have a squirrel cage which is used for starting the motor, and the motor accelerates, and then we have embedded in the rotor we have rare earth magnets which are able to synchronize the rotation speed of the motor to the speed of the rotating field. So these motors have high efficiency, and because they have high efficiency, they have a lower temperature, lower running temperature, and they have high reliability. We have two concerns about these motors. Number one, high cost in relation to the conventional induction motor, significantly high cost, and also the torque behavior. So the efficiency is higher, as you would expect, when comparing an IE3 with an IE4 motor, a reduction of about 20% in the losses. But when it comes to the starting performance, we have torque oscillations. And I must say that in my own experience, we already broke some couplings with the starting of this type of motors when connecting to different types of loads. So it's important to be aware that you need to take precautions if you have some delicate mechanical equipment, that you need to ensure that there will be no problems when starting this type of motors. When the permanent magnet motor is driven by an electronic controller, you can achieve very high torque to weight ratio, and you can achieve the largest torque at zero speed, which is an inherent advantage when comparing with induction motor. And this is one key advantage of permanent magnet motors driven with variable speed controls, is that you are able to have a very large starting torque, which in many applications it's very useful, avoiding the use of mechanical transmissions. This is the torque and power curve of electric motor using in one best-selling electric vehicle. Actually, you can see, comparing with the previous slide, that the manufacturer is basically cutting a part of this upper part of the curve, because what the manufacturer wants by cutting here this part with the highest torque is avoiding overheating of the motor. So basically, it just limits the current, and by limiting the current, you limit the maximum torque. Theoretically, the torque of the motor would be possible to go higher. So we see that in an electric vehicle, maximum torque is provided almost constant until you reach the base speed, and then you have a constant horsepower operation. So this is a type of torque and power characteristics which are common in electric vehicles, which, by the way, most of the electric vehicles on the market are using permanent magnet synchronous motors. Here I explained a couple of minutes ago that the difference in performance in part load operation in reduced speed, reduced torque situations between permanent magnet motor and induction motor is wider when you are using part load operation, and this graph shows this type of illustrates this widening gap when you are reducing the load on the motor. I also mentioned that ferrites are much cheaper than rare earths, and some manufacturers have been creating some new designs in which they are able to use ferrite magnets to achieve this higher performance, and this is an example of an American manufacturer, which Novatorque, which is has produced a super premium motor, i4 motor, using ferrite magnets. And here the idea, of course, is you can achieve the very high performance, and at the same time you are not paying the penalty for the high cost of the rare earth magnets. So this type of strategy is being pursued by other manufacturers. And one other product on the market with ferrite magnets claiming to meet I4 and even I5 is this motor, which uses ferrite magnets made by Hitachi, and they use amorphous steel laminations. So by using amorphous steel laminations, they slash the magnetic losses, and they are able here to have a motor that is lighter, more compact, and higher efficiency than the I3 motors, which normally you associate higher efficiency with a bulkier motor. This is not the case. In this case, because of the design and because of the better materials, this is a very compact design. So another type of motor which can achieve efficiencies, super premium efficiency, is the switch reluctance motor. And this motor has very simple construction. Basically, it's a rotor made with, it only has magnetic steel and steel in the rotor with salient poles, and you create a rotating field with the stator, and basically the rotor is going to track in synchronous this type of rotor. Because of its construction, is very robust and can be used at very high speeds. 20,000-30,000 RPM are possible. So it's a motor for premium applications like high-speed compressors, vacuum machines. This is type of applications. Is a specialized motor. Has not been so popular in terms of number of manufacturers, but it's an option for which has been popular in some niche applications. So low cost of manufacture, very robust because there is nothing to go wrong in this rotor. Of course, you'll have to replace the bearings after several tens of thousands of operating hours, but it's very robust design. Another relatively newcomer, as maybe 4 years, 5 years, is the synchronous reluctance motors. And in the synchronous reluctance motors, what you have is a stator very similar to the induction motor. You have also the three-phase windings, which create a rotating magnetic field. But in the rotor, you have, instead of having the squirrel cage, you have a rotor in which you have the steel laminations cut in such a way in which you create some poles. So this type of design, because it's synchronous, when you compare the losses from one motor to the other, you see that the losses which in the induction motor are the rotor losses, which I'm pointing here. When you change to the synchronous reluctance motor, basically you don't have these losses. So this can represent more than 20% reduction on the losses. So, and you can play with this type of load reduction in two ways. Either you can produce a more compact motor, or with the same frame size, you can increase the efficiency class of the motor. And in Europe, there are already at least 3 large manufacturers we have now a line of synchronous reluctance motor. So this motor, in terms of manufacturing costs in large quantities, should be cheaper than an induction motor because you don't have the squirrel cage. So in terms of active materials, has less active materials than a competing induction motor. So, and it's more efficient and is a synchronous motor. So in terms of, it has low inertia because you don't have the cage, so the rotor is lighter, so good acceleration performance, lower manufacturing cost, and what are not the so good parts? I would say the main disadvantage is that this motor cannot be started directly from the grid. So you need to have an electronic controller to start a motor and to control the speed. But if your application is a variable speed application, like controlling a pump or a fan, then it's no problem, because in any case you need a speed controller, and the speed controller can be used to start the motor. Interestingly enough, there is at least one company that has been trying for the last couple of years to have a line start version of this type of motors. And what they are doing, and this was shown in the last EMOD conference, is that what they are doing, something that's pretty obvious, is that they, what can be done is, in this cage, you can embed a squirrel cage. And if you embed a squirrel cage, you basically have an hybrid rotor. You have a rotor that, in which the starting torque is produced by the currents induced in the squirrel cage, and then when the rotor speed approaches the synchronization speed, you have that the reluctance poles in the rotor are able to lock the rotating field. But this is not, to my best knowledge, is not yet a commercial product, and we'll see what happens, but several manufacturers must be working, because this, of course, would be a welcome development for this motor to be able to operate directly from the grid. My feeling is that this motor, this hybrid rotor, it will be difficult to match the starting torque of a conventional induction motor. It may be able to start loads with low inertia like a pump, but it will be a different story for higher inertia loads. In any case, this is something that's ongoing. The development of line start synchronous reluctance motors. So these motors run cooler, they have lower losses, and if they run cool, you are going to expect that the key components in the motor that are affected by temperature, like the bearings and insulation in the windings, is going to last longer. So this is good news. So again, this is another slide looking at two rotors, the two motors of the same size, and looking at the comparison. So here we are speaking of two motors having the same stator and looking at the distribution of the losses. And again, here we see basically that the rotor losses, magnetic and copper losses, Joule losses, are basically reduced to zero, and the loss reduction is between 10 to 20%. So this type of improvement is even larger at lower loads. So basically, this is an I4 motor made by another European manufacturer, and it shows that the part load performance difference between an induction motor and this synchronous reluctance motor is also larger than when you are at full load. At full load, you may have 2-3%, but when you are working at part load, this gap widens, and this has to do with the distribution of the losses in the induction motor. So in terms of what the future is having for us, we are seeing that the manufacturers are looking at a variety of technologies to improve motor efficiency, looking at permanent magnet motors, both with high performance, high cost materials, and low cost, moderate performance materials. And we see here a study that we did with Hugh Faulkner. I noticed that Hugh is one of the persons attending this webinar. We did a study looking at motor total life cycle cost, looking at different types of motor construction, and we see that for motor operating a large number of hours, it really pays to move in the direction of at least super premium efficiency. So we see here that for I5, I think if I5 is able to be achieved with lower cost permanent magnet motors, permanent magnet motor materials, I think it may also be possible, but right now I5 motors are still quite costly. So, and in terms of cost effectiveness, in terms of life cycle cost, of course a key parameter to analyze this life cycle cost is the number of operating hours. So the larger the number of operating hours, the more cost effective is the higher efficiency technology. And variable speed applications, motor with variable speed applications, it's about half of the motor applications seem to benefit from variable speed, variable torque controls. So, and this, for this type of applications in which you need variable speed, variable torque control, I think this is where synchronous technologies have inherent more advantages. So I suppose I have reached 40 minutes speaking time, and I suppose now I should stop for having some questions by the participants. Thank you for your attention.